Okay, so please settle down. Let's get started. Okay, so a few important things. Okay, have you all registered for your tutorial and lab groups? Registered or not registered? Okay, because suddenly I don't see any registration in the IBLE. Okay, so I'm checking with the IT team on what happened. Okay, so far I don't see any registration for tutorial and lab. So if you haven't, please make sure you register for your slots. Okay, as you know, it is a lab intensive course, so attendance and participation in the labs as well as tutorials all form your marks. Okay, so if you haven't registered, you must register. Okay, so you cannot skip your lab or your tutorial. You must register for one of the slots. Okay, so as much as possible, please stick with your slot. Okay, you cannot jump around unless you have a valid reason. Okay, so if once you register, you stick with your slot, so you make it easy for us to do your grading and your marking. Okay, so again, this week's lecture we are slowly getting in. So this week's lecture is also fairly simple, straightforward. Okay, so shouldn't take more than an hour or so. Okay, so it's still getting you into the mood. Okay, next week onwards, things will start to pick up a lot more. Okay, so if you are, so again, this is a CG module. Okay, so again, it means that there is some sort of expectation on some prior knowledge. Okay, so if you look at this set of material, towards the last part, there is some supplementary material given. Okay, but actually, it is sort of expected that you already know it, but in case you do not know it, you can go through that material. Okay, so those are some of the hardware aspects and so on. Okay, so we will not cover that in the lecture, so if you are unfamiliar, then you can go through those supplementary material. Okay, so let's get started with I/O. Okay, so if you are experts in Arduino programming and so on, maybe this can be a bit boring, but still bear with me. Okay, so that everybody understands some of these concepts. Okay, so what is I/O? I/O, again, very simple, very fundamental. They are input-output components for your system. Okay, so whether it's a real-time system or whether it's just a normal microcontroller-based single-threaded system, you're always talking about input and output. Correct? Okay, so any system has to have some form of input and it will do some processing and generate some form of output for us. Okay, so even if I just take this laser pointer, correct? Okay, so at any point of time, it is still waiting for the user to do something. Correct? Press some button, okay, or toggle some switch, and once it detects an input, it must process it and generate some output. Okay, either it must send a signal to the system, okay, to the PC to change the slide, or you might activate the LED laser to shine, and so on. Okay, so most of the time, this ability to access I/O is a very fundamental requirement. Okay, so of course, towards the end of this slide, you will see that even though we are using Arduino board and so on, we are not going to be using the sketch programming. Okay, in lab 1 next week when you all start, the first part, I already uploaded the material, so if you can actually download the software and do it on your own as well, even before the lab start. Okay, so there's a lot of steps involved in setting up the libraries and folders and so on. So that is a bit tedious, but once everything is set up nicely, then it's a bit easy. Okay, so you will see later on some of the sample code that we're going to be writing. We are not going to use Arduino libraries. Okay, we are going to just use it for the first part of the lab just to make sure everything is correct. Okay, that your system is set up correctly, your hardware is correct. Subsequently, we're going to do actual microcontroller programming. Okay, some of you may have already done something similar in other modules. Okay, if not, if you have, then it's good. If not, it's still, we are starting from ground zero, so you don't need to worry. Okay, so let's look a bit at some of the sensors and actuators that you are going to be dealing with. Okay, so of course, when you talk about our PCs, our traditional system, you talk about keyboard, mouse, and screen. Okay, but now we are talking about embedded system, okay, which basically means what? Okay, so when you say embedded system, it actually means it is a mini computer concept, alright? Okay, that means you still have a microprocessor or a controller, and you're dealing with certain limited input-output. Okay, so instead of having a full-fledged keyboard and a mouse and so on, you are dealing with maybe some buttons, some switches, and some other different forms of output. Okay, so of course, over the years, even embedded devices have become much more advanced, correct, with full touchscreen and so on. Okay, so of course now there is a blurring of sort of boundary between what is a PC and what is an embedded system. Okay, so let's look at inputs. Okay, so our most common input is of course your digital switch. Okay, so on-off switch and push button switch and so on. Okay, so in our Sparks Fun Inventor Kit that we're going to issue you, okay, you will have some of this hardware inside which you can play with, okay, which will be fun. Okay, so of course, like I said, this is a CG module, which means that there will also be some minimal hardware involved as well, correct? That means you are still expected to know how to wire up some of these components yourself and connect to the microcontroller. Okay, so it's not just on board, everything is there, you still need to do some hardware. Okay, so digital input using switches like this is what you're going to use in the lab. Okay, then you also have encoders. Okay, those of you who have played with cars and remote control cars, they give you feedback. Okay, encoder is what? Encoder is nothing more than a disk. Okay, when you talk about encoder, it's nothing more than a disk with small holes or slots. Okay, so if I look at this disk from a cross-sectional point of view, it's actually just like this. That means you imagine like it's a thin pizza. Correct? The thin pizza, it turns sideways, but a lot of holes. Okay, then an encoder, what will it do? You have a transmitter and a receiver on both sides. Okay, so what the whole idea behind it is when the wheel is spinning, when this encoder disk is spinning, when I have a transmitter on one side, okay, when I have a transmitter on one side and I have a receiver on the other side, okay, so when it reaches the hole, the light will go through, correct? Okay, when it reaches the covered space, the light will get blocked, correct? Okay, so as the disk is rotating, okay, the light will occasionally shine through and occasionally get blocked. Okay, so this continuous movement and rotation will generate this series of pulses for me. Okay, so when I look at these pulses, when I connect these pulses to a microcontroller, and then I do some counting and so on, I can actually keep track on how much my disk has rotated. Okay, so that is how an encoder works, which is used extensively in robotic system whenever you have mechanical movement. Right? Because when you turn something, when you move something, you want to know exactly how much it has moved. Okay, so this encoder will give you the feedback, okay, to know how much you have actually moved. Okay, so of course, when you were talking about switches just now, one of the issues that we have to deal with is bounce. Okay, so if you connect up a switch, okay, let's say I connect up a switch. Okay, I take this connection and pass it to microcontroller. So if I connect this thing, this line here to my microcontroller, how will the switch behave? By default, it's 1 or 0. By default, this is 1 or 0. Hey, you all should know. 1 or 0? Don't know, in between. Any brave soul want to guess? By default, I connect this pin to a microcontroller. It will read as logic 1 or logic 0. 1 or 0? Nobody want to answer. Then I must put this in the midterm, right? Huh? Don't make me put this in the midterm, where they will laugh at the midterm. Okay? By default, this is what? This is connected to your VCC, so it's 1, correct? When I close the switch, I will create a short circuit to ground, so it becomes 0, correct? You are looking at me as if you are talking in Japanese or what, you know. This one is, again, like I said, some of this hardware is assumed that you all know, because this is a CG module and level 2 module. So some hardware is already expected from you. Okay, so if I connect a wire by circuit like this, and I connect to a microcontroller and I press the switch, okay, so rightfully, by default it is 1. When I press the switch, it should go low. Okay, so of course theoretically you get a very nice pulse, but in reality you don't get that. What you will get is you get something like this, okay, before it finally settles down. Okay, that is the reality. If I hook up an oscilloscope, to this pin over here and I observe the waveform, this is what I will see if I zoom in. Okay, why? Because even though physically we think we only press 1, but mechanically it will generate a lot of bouncing when the contact closes. Okay, so at the mechanical level, there will be a lot of bouncing that is created. That's what we call the contact bounce. Okay, so when this contact bounce occurs, it can create a problem for us. Correct? Why? Because in our microcontroller here, we would have written some code, correct, to capture the event when the pin goes from high to low. Correct? Okay? But what will happen? I will capture one event here, I'll capture one event, so many events, correct? Okay? So I can very easily mistake one button press to 3 or 4 button press. Okay? It's a very common thing that you can have. So what I need to do? I need to do a debouncing. So a debouncing is a very simple thing. You just want to make sure that when I detect a switch being pressed, I must make sure I only detect one event. Correct? I cannot go and consider all the bounce as multiple events. Okay? So of course, the easiest way is what? You insert a delay. Correct? The most easiest way is insert a delay. That means when I detect the first pass, I delay for a while. Correct? How much to delay? No matter what we tell you, you always say trial and error only. Correct? You just try until you're happy. One time press, one time trigger, okay, happy. Correct? So maybe you try for 50 milliseconds, maybe you try for 100 milliseconds. As long as you work for your hand, your finger, you're happy already. Correct? Okay? So, in a software technique, you just put a delay. Okay? So, of course, if you want the hardware approach, there are a lot of different hardware circuits available. Okay? So, I'm not going to go in hardware circuit, but hardware circuits can use logic gates, can use latches, can use capacitors. Okay, so there's a lot of hardware solutions as well, okay, to overcome debouncing problem. Okay, so that is, of course, digital input. In our kit that we're going to give you, you're also going to play with a lot of analog sensors. Okay, so analog sensor means what? When you say you are a sensor, it means you are trying to detect some physical or environmental phenomenon, correct? And you are converting it into an electrical signal, correct? That your system can use. So when you say it's an analog sensor, that means that signal that you generate is an analog signal. Okay? So in most cases, most analog signals will generate a DC voltage. Okay? So exactly what is the voltage, how we respond, it all depends on the device that you are going to use in your system, correct? Okay? So take for example, if I use a temperature sensor, this is a temperature sensor here. Okay? So this temperature sensor, basically what it does, it generates a DC voltage signal. Okay? When the temperature changes. Okay? So when you put this in an environment, you need to know how to connect this. So how do I know how to connect the pins? I got 3 pins there, correct? How do I know which pin is VCC, which pin is ground, which pin I connect to a microcontroller? What must I do? Ini, mini, miny, mo. Try my luck. Then you see smoke means you throw away. Pretend you never see the smoke. Then try another one, correct? No, don't try your luck. What must you do? You must refer to the data sheet, correct? Every component that you have, that you purchase, you must make sure it comes with a data sheet. If you don't have the data sheet, it's as good as you don't know what you're buying, correct? Okay, because you have no idea how to connect the device. Okay, so you must have the data sheet. Who is responsible to give you the data sheet? Not me, the manufacturer of your product. Okay, so if I buy from a company, that company will have a website, they'll put all the data sheet there, you must go and download. Correct, then they'll give you all the detail, how to connect this, what is the voltage rating, what is the current rating, what is the temperature, and so on. Okay, so you must look at the data sheet to know how to connect your devices to your system. Okay, so this is a flex sensor. Okay, so when you bend it, okay, you will see the voltages changing. Okay, and of course this is your ultrasonic sensor here. Okay, very commonly used in a lot of systems. Of course all our cars have it now, correct, in your rear sensors and so on. Okay, so again, a lot of the devices or sensors you play with in your kit that we give you is quite interesting for you to learn a lot of stuff. Okay, so you're also going to give you a potential meter. Potential meter you all got play before, right? It's nothing more than just a variable resistor. Okay, so it gives you the option to change the resistance by turning the knob. Okay, then you got a photoresistor. Photoresistor means what? It changes the resistance based on the amount of light that you shine on it. Okay, so when I shine, if I use my handphone to shine some light on it, okay, the resistance between the two LEDs will change. Okay, so again, you can play with that. Okay, so just now all the while we talk about analog sensor. Okay, so of course, our microcontroller itself is a digital system, correct? A digital system. So if I want to take any of these devices, if I want to take this temperature sensor, and if I want to connect this to my microcontroller pin, okay, I need to be able to digitize it, get a digital representation for this value that I get. Okay, so how do I do it? I need to do a conversion, correct? Between analog signal and digital signal. Okay, so that conversion is basically A to D and D to A. Right? Okay, so whenever I want to bring a system, a signal into my microcontroller, I need to make sure it's digitized for me to take the data in, process it. Once I have an output, I know what to do, then I can reformat it back to analog on the output side if it is necessary. Okay, so what is analog to digital conversion? Is nothing more than just sampling. Okay, so what you need to do is you sample the analog signal, okay, at a preset frequency, and when you sample it, you get a digitized output here. Okay, that represents the value at different points. Okay, so that is the whole idea behind A to D conversion. Okay, so this A to D converter, in some microcontroller, you may already have this feature inside as well. Like our Arduino Uno already has some pins that can do A to D conversion. Okay, that means if I have an analog signal at my temperature sensor, I can directly connect to my Arduino, and inside the Arduino, I can program it to do the conversion for me. But some microcontroller, maybe it's a cheaper version or a low-end version, they may not have A to D conversion. Okay, so in those cases, you may need to have a separate A to D chip. Okay, so there are also dedicated chips out there that will do specific operation for you if your microcontroller does not support it. Okay, so again in A to D, what are you trying to do? You're trying to map your input voltage signal, okay, usually in 0 to 5 volts to an output. Okay, that means if I have 8-bit ADC, okay, and if I say that my input to my ADC is 0 volt to 5 volt, and my output of my ADC is 8-bit, that means 0 to 255, correct? That means what am I trying to do? What is the ADC trying to do? It is trying to map an input analog signal from a specific range to an output bit pattern within a certain range as well. Okay? So that is what we call the resolution. Okay? So it means that eventually I cannot map every analog signal to a digital signal, correct? There will definitely be something that is lost along the way. Correct? There is something that is lost along the way, and that is your resolution. Okay? So, if I have, for example, 5 volts range, okay, and I only have a 2-bit ADC, okay, if I took this example here, I have a 5 volt range, 0 to 5 volt, and I only have 2-bit ADC here. So if I only have 2-bit ADC, how many output can I have? Only 4 different output, correct? Okay, I can only have 4 different outputs. So that means each of this output is separated by 1.25 volt, correct? 5 divided by 4. Okay, so the number of bits that I have, when I have more bits, it means I have more resolution. Okay, when I have more resolution means what? Okay, the accuracy is higher. Okay, so you have to imagine that if now I only have 0 to 5 volt and I only have 4 output, that means 0 volt is here, 1.25 volt is here, right? And so on. Okay, so it means what? That means if I have an input of 0 volt, it will map to 0 volt. If I have an input of 0.5 volt, it will also say 0 volt. If I have an input of 1 volt, it will also say 0 volt. Correct? Because your resolution is too little. You have too few steps, so it cannot capture all the changes in your analog signal. Okay, so if I want to be able to capture more and more accurately, I need to have a higher number of bits. Okay, so that I can capture all the smaller changes at the input side and map it to my output side. Okay, so this is your ADC quantization thing that you need to look at. Okay, so of course, in reality, if possible, we want to save all this hassle, alright? Of analog signal, A to D, then you lose your resolution, and then you try to process a signal that is not so accurate. Okay? So the best is what? The best is if I can start off with digital, correct? Okay? So the best solution is what? When you are doing your own project, your final year project or whatever hobby project, if I can stick with digital all the way, then it solves all my problems, correct? Okay? So all these sensors that you see here, they also have analog version plus digital version. Okay? That means digital version means the same sensor, it may look the same, but it can output a digital stream for you. Okay? That means it looks exactly like this, but in an analog sense, it will give you an analog signal. Correct? But the same sensor, if I buy the digital version, I'll get a series of bits, ones and zeros. Okay? So if I can capture, or if I can get the same functionality with a digital device, might as well go with the option, correct? Okay, so I don't need to do ADC, don't need to worry about anything. I straight away take the digital data and I can process it. Okay, but you have no choice, there is no digital option available, then you still have to go through this process of A to D, all this quantization, then finally take the data and then process it. Okay, so of course that is the first part here. So what we saw is this part, the sensor coming into your system. Okay, so of course, when the data come in, you process it, you will decide what I need to do with it. Okay, and after I decide what I want to do with it, I need to generate some output. Okay, so the output devices are also known as actuators, okay, in common term. So when you are going to send an output signal, depend on, again, whether it's digital or analog. So in digital sense, of course, the most common one is your LED. Okay, so again, LEDs are good, a very good way of telling us whether things are going according to plan and where your code is executing and so on. Okay, why? Because they give us the most easiest feedback. Okay, again, you must remember that you are writing a code that is going to run on a board, not on your PC. Correct? On your PC, no problem, everything also printf. Correct? Print on the screen, print on the console. Okay, but once you transfer to embedded system, there is no print, there's no console. So you need to use this kind of LEDs and so on to give you an indication. Okay, is it correctly executing, or did my code get stuck somewhere in some infinite loop and I don't know what's happening? Correct? Okay, so LEDs are very good for that. Okay, of course you also have our analog actuators, DC motor plus servo motor. DC motor, very common, almost all toy cars, remote control cars, all use DC motor. Okay? Why they use DC motor? Because it's the most easiest and cheapest to use, and no need to use any control circuitry. Why DC motor? All I need to do, even if I don't know anything about electronics, I just connect a battery, it will spin already. Correct? Huh? So even if I don't know anything, I just connect a battery, a DC motor will spin. Okay, but other motors are not so straightforward. Okay, but DC motor is very straightforward. So as long as I apply power, current flows, it will start to work. Okay, so most toys, most simple systems use DC motor for their control. Of course, if you want a bit more accurate control, you can use servo motor. Okay, servo motor works on the principle of PWM. What is that? We will look at it in a while. Okay, but servo motors allow a bit more accurate control and positioning of your motor. Then you also have another one called the stepper motor. But all these are a bit more tedious in a sense that you need control circuit, you need additional hardware to control the movement of the motor. Okay, so in stepper motor, you actually move the motor in step. Okay, so every time you do a step, you move by maybe 12.5 degrees or 5 degrees and so on. Okay, so it moves in a very granular motion. Okay, so what is PWM? Okay, so PWM, I think briefly I talked about it last week. Okay, so the most important idea of PWM is how do I generate an analog signal from a digital system. Okay, so you have to remember that in our microcontroller, what do we have? Okay, in our microcontroller, we have normal input-output pins. Okay, if I configure a pin as an output, I can drive it to be high or I can drive it to be low. Correct? Okay, if I drive it to be high, I get a voltage. If I drive it to be low, I get another voltage. Okay, all normal GPIO pins behave like that. On the input side, we just saw that I have the ability to take an analog signal and bring it into a microcontroller using my analog to digital converter module. Okay, so on my output side, I can generate digital output logic, 5 volt, 0 volt. On my input side, I can take in 5 volt, 0 volt by switches, for example. I can also take in an analog signal, correct, that is always changing. Okay, but how do I generate an analog signal as an output? Okay, how do I generate analog signal as an output? So the only way you can sort of mimic that is through a PWM. Okay, so what does a PWM do? In PWM, what you are trying to do is you are trying to generate this kind of signal here. Okay, so in order to generate this kind of signal, what we are going to do is we are going to generate a series of pulses. But you can see that the pulses that we generate have width that keep on changing. Okay, why? Because the width, okay, the width of the pulse is the one that will actually determine the voltage at any point of time. Okay, so that is the whole idea behind PWM signal. Okay, so the concept is very simple, only 3 parameters: the period of the pulse width, and duty cycle. Okay, so duty cycle is defined as the pulse width. Pulse width is what? Pulse width is the time that it is high. And this is your period, the whole repetition. Okay? And that is how you get your pulse width duty cycle. And how do you translate this duty cycle? If your duty cycle is low, that means you are on for less time, off for more time, correct? Okay? So when your duty cycle is low, it means that your eventual voltage is also going to be low. Correct? Because I'm on for lesser time, off for more time. Okay, when your duty cycle goes up, your average voltage also goes up. Okay, when it's 50%, of course it is half-half. Okay, when it's 90%, it's always going up to full. Okay, so by using PWM, you are able to generate a analog voltage. That means now what? My microcontroller pin, by doing PWM, I can now generate voltages that are in between 0 and 5 volt, correct? Previously it's only 0 volt or 5 volt. Okay, now I can say that this is maybe 1.2 volt. Maybe this one is 1.9 volt. This is 2.5 volt. And this is 4.1 volt maybe, correct? Okay, so I can now generate voltages that are in between 0 and 5 volt by using PWM technique. Okay, and why is this important? Why is this critical? Because I can now use this same technique to control so many things at a step-by-step level. Correct? Okay, so for example, I want to control this DC motor. So previously, if I connect my DC motor again directly to a battery source, okay, it will either on or off, that's it, correct? Okay, it's either my motor spin or my motor is off. Okay, but now instead of connecting it to a DC source, okay, I'm connecting it to a PWM source. Correct? So now it's not just on and off. I can now say move a bit faster, a bit slower. Correct? The same thing. Instead of a DC motor, I can connect a LED. Correct? Now I can do dimming function. Correct? I can say from full brightness, slowly dim down. Or slowly go up to full brightness. So I can do a lot of applications now that I am able to generate an analog equivalent for my microcontroller pin. Okay, so again, another use is in your servo motors. So in a servo motor, by using pulses, you are able to set exactly where the motor is supposed to be. Okay, so again, so no need to worry too much. In your lab, if there's a chance, you will try it. Okay, so now let's look at the software interfacing part. Okay, so the software interfacing part is the one that is critical. Why? Because one side you have hardware, correct? The other side is your software, correct? That is why you all are computer engineers, correct? You are the best of both, correct? You can do the hardware plus you can do the software. Even if you don't know, you just say you know, correct? In a resume, don't say I don't know anything. You say you know everything. You just go for interview and then you see how you can smoke your way through, correct? Okay, so first thing, your I/O registers. Okay, so along the, of course your microcontroller has a lot of registers, a lot of functionality, okay, but we will only cover bits here and there, okay, depending on the lab exercises. The rest of it, you are always free to try it out on your own, no problem. Okay, so I/O registers refers to a set of registers that you need to program in order to make your device work. In your Arduino sketch programming, correct? When you connect an LED to a particular pin, what do you say if I want to set it to be output? What is the command you use? Sorry? Pin mode, correct? In your Arduino, if you recall, in your Arduino sketch, there is this thing called pin mode. Okay? Okay, and what does pin mode do? It is supposed to set a particular pin to input or output. If you have tried Arduino, you know. Okay? But again, like I said, that is sketch programming. Okay? And what pin mode actually does, you do not know. Because it hides a lot of things from you. Okay, so today we are going to unhide those stuff and learn actually what it does at the lower level. Okay, so within every microcontroller there are a lot of registers. Okay, and all these registers help us to control and configure all the various functionality that the microcontroller gives us. Okay, so for an I/O device, again there are some registers. The input register. So if I say I want to read from an input pin, I need to read from a particular register. If I say I want to write to a pin to control the LED or something, there's also an output register. Okay, then of course there are status register to tell me some information on what is the status. This is used in some situation. Plus control registers. control registers are, in this case, your data direction register, whether I want to configure it to be input or output. Okay, so we're going to look at some of these registers. Okay, so in terms of processor architecture, okay, I'm not sure if you've studied microprocessor architecture module or anything equivalent, okay, but a processor looks something like this, architecture. Okay, so again, we are not going into this detail. The whole detail of this is another module that I teach, CS2100. If you want, you can take. But I don't know whether you all are taking an equivalent. Okay, so there's a few equivalent modules, correct? Because CS offers some, the engineering side also offers some. Okay, so there are equivalent modules. In CS, we call it 2100, where we go into computer architecture. Okay, so in a computer, if you look internally, what does it have? Again, the heart of it is your CPU. Okay, the heart of it is your CPU, which is your brain, correct? The brain of the system. Okay? But of course, the brain of the system cannot function without memory, correct? It needs to know what is supposed to execute, what is the code is supposed to execute, and all of that is inside some memory here. Okay? And again, ultimately, every system is meant to monitor some input, do the processing, and give some output. So there must also be some input-output. Correct? Okay? So this is again a very, very simplistic high-level view only, just to give you the idea. So in a system, there is a CPU, there is a memory, there is input-output devices, and of course, to connect them together, we have buses. So we have memory bus, we have I/O bus. So a bus is just a collection of wire for us to know which device we want to talk to, who we want to communicate with. Okay? So there are different types of I/O devices that are architecture that are available. Okay? The two most popular ones are this, called isolated I/O and memory mapped I/O. Okay? So what is this? We will cover that in a while. Let's go for a short 10-minute break. Okay? So go for a short 10-minute break. Now it's 4:40. According to that, 4:50 we will resume. Okay, so let's carry on. Okay, so in terms of the bus, okay, so there is two types of buses, okay, architecture. One is called isolated I/O, the other is called memory map I/O. Okay, so again, no need to worry about the details of how it's implemented and so on. This is just to give you an idea only. Okay, in isolated I/O, okay, so what does it mean? That means your input-output devices, okay, input-output devices are separate or having a separate address space compared to your I/O address space. Okay, so it basically means that all my input-output devices, I can only map to certain addresses within my system. Then your main memory, your secondary memory, and so on, that is mapped to a separate address space. That is how isolated I/O works. The other option is your memory map I/O. Okay, in memory map I/O, what they do is they say the full address space. That means from the start to the end, everything is integrated together. Okay, as one continuous address space, and you can choose where you want to put what. Okay, and the difference in the architecture also means there is also some difference in the way you write programming. Okay, if you have studied assembly language programming, you know that we go at the register level. Correct? In isolated I/O, there are separate instructions for input-output devices and there are separate instructions for memory devices. In memory map I/O, they use the same instruction whether it is an I/O device or memory device. Okay, so again, if you have not studied computer architecture yet, then do not be too worried about this bit of information. Okay, this is just to give you an idea on how things work from the processor perspective. Okay, so let's go on to what you are going to be actually doing, okay, for your Arduino, okay, and the I/O. So this is your Arduino Uno platform. Okay, so again, most of you may have tried it and played with it before, okay, either in some hobby, some project, okay. So again, when you have tried it before, you have used your Scratch programming, okay, but now we are going to go in and explore actually what is going on at the microcontroller level, okay, that means at the register level. Okay, so again, this is your Arduino Uno. It has a lot of features and so on, but let's take a look, okay, a bit at what actually it has. Okay, so Arduino Uno is the brand name given by the Arduino company, correct? But actually the microcontroller is your Atmega 328P, okay, from Atmel. Atmel is one of the companies that produces microcontrollers. Okay, so of course we all know the most common one which you use in your desktops are your Intel, processors and so on, or AMD processors. Of course, for the embedded system, you have a few popular processors like ARM processor and so on. At the embedded level, you also have things like Atmel, PIC, Motorola, and so on. So there's a lot of companies out there that produce microcontroller chipsets for a wide variety of embedded applications. Okay, so Atmel is one of it. So your actual microcontroller is a 28-pin 8-bit microcontroller. Okay, so when you say this is an 8-bit microcontroller, means what? When somebody tells you this is an 8-bit microcontroller, this is a 16-bit, this is a 32-bit, what are they talking about? What does the 8-bit refer to? What does it refer to? It refers to the size of data that you can process at any point of time. Okay, which translates to a few things. Okay, that means it translates to the size of your registers. That means all your internal registers are 8-bit. That means your data bus is also 8-bit. Okay, that means at any point of time, I can take 8-bit of data and I can process this 8-bit of data inside. Okay, which means intuitively you can say why a 16-bit is more powerful, a 32-bit is more powerful, a 64-bit is more powerful, correct? It means at any point of time, I can deal with that much of data. Correct? So When you say 8-bit means at any point of time, I can only deal with 8-bit of data. I can do my computation, I can do my calculations, whatever on 8-bit of data. Okay, it's based on a RISC instruction set. Again, we're not going to go into details here, but there's only two types of instruction set out there, RISC and CISC. RISC means reduced instruction set. CISC is complex instruction set. Okay, so they are just two different instruction sets depending on the type of programming that you want to do. It runs at a particular frequency of 20 megahertz here. Okay, and it has all these subsystems inside. Okay, so I explore some of this along the way in your labs as well. Okay, so this is the internal block diagram, okay, of the Atmega 328P. Okay, so again, if you look at it, you can see that the CPU is there, like just now what we saw. There is your data bus, correct? Okay, and you see all your subsystems connected. Okay, your subsystems are what? Your GPIO ports here, port B, port D, port C, and so on. Plus you have some memory here. Okay, then you have other peripherals as well. Your timers, your analog comparator, your UART. Okay, so again, we will explore each of this or some of this along the way. Okay, in some of our labs. Okay, for now, today's objective, you're going to look at the ports, GPIO port. Okay, so again, the memory, we have some memory. So this memory again is important for you because you need to know how big your application is going to be. Correct? Because sometimes you buy the Arduino Uno and then you write, and then eventually you realize when you compile fail. Why? Because not enough memory. Correct? Your program is too big to fit onto the microcontroller's memory. Correct? Then what do? You curse and swear first, correct? Then you make a wrong decision. Then after that, what do? You ask your supervisor, can I buy a different microcontroller, whether I got budget or not? Correct? And then you hope and pray that everything still works. Correct? Because sometimes you change microcontroller things, some things may work, some things may not work. So again, you need to make some changes to your code. Okay? So again, this memory is important, okay, to know how much or how big your code size can actually be. Okay, so Arduino, again, these are the general idea of the input-output. You will look at it along the way. And what we're going to look at is GPIO for today. So again, as we saw, GPIOs can be connected to any devices. Okay, can be input devices like a push button, can be output devices like your LEDs. Okay, and in general, you only have on or off. Okay, 1 or 0, whether it's input or output, unless you are using a PWM pin, then you have the analog output functionality. Okay, so what you need to know is how do I connect up these GPIO ports on the Arduino. So where are these GPIO ports located? They are located on the headers on the right side here. Okay, so in the Arduino Uno board itself, they have sort of nicely brought out these pins for you and connected them through the headers, so it's easy for you to connect. Okay, but actually, your microcontroller, if I look at it as the full schematic, what is this? This is the whole full schematic. Okay, this is just to scare you only, don't worry. Okay, so if I look at the full schematic, okay, why is this important? Why is this important? Because ultimately, you only want to know about the microcontroller, right? Okay, but the board itself has a lot of things. The board itself has a lot of things. Okay, so now anybody can tell me, where is the microcontroller here? Which one? There's only two options here. Okay, so there's only two options. Either option 1 or option 2. 1 or 2? Sure or not? Because you'll see the slides, right? Okay, because the slides already give you the answer. Okay, so there's only the microcontroller, which is the Atmega 328, is only the number 2. Okay, so that is actually the heart of the system. Okay, the rest of it is there because you have bought the board and the board is providing other functionality. Correct? Okay, so again, why is this important? Because eventually, yes, you have the Arduino Uno, you prototype your project, it works, everything is good, you are happy. But what if, let's say now you say, I want to sell this product, correct? I want to commercialize it, since it's a good product. All my friends will sure buy from me, I'll force them to buy, correct? Okay, and you want to commercialize it. So what do? You must think of how you can create a cheaper version, correct? You don't want to sell your product with the Arduino Uno board inside, correct? It's a waste of money. You only want to sell with the microcontroller board inside, correct? The microcontroller which runs your code. So you want to strip down this whole thing to the bare minimum, correct? So what is the bare minimum? What is the bare minimum I need? Okay, so the bare minimum I need, okay, is just my microcontroller. Okay, I need my power and I need my clock. That's it. That's all I need. Okay, so you can take this chip, put your crystal there, put your power supply there, and it will just run. The rest of it is just there to make your life easy while you are prototyping your project. Okay, but once your design is done, your software is done, everything is done, you want to create your own PCB, you want to create your own hardware block, you don't need all that anymore. Correct? You can strip it down to the bare minimum and you can shrink it to a very small size. Okay? So that is the eventual aim why you need to know. Okay? Okay, why looking at the schematic and understanding how it is connected helps you. So that you know what to do, okay, when you want to move your project to the next level. Okay, so these are the actual pins on the Atmega 328P. So you can see that as any IC chip, okay, the pins are numbered according to their position. Okay, and at any point of time, you also see that you have a lot of functionality, correct? Most pins are multiplex. Multiplex means what? That means you have a lot of functions on the same pin, correct? Okay, so you must be able to select the correct functionality that you want. Okay, the correct functionality that you want. So, again, all this boils down to how you program those registers inside. Okay, so by programming the register, you are able to select, okay, which functionality do I want? Do I want to use this pin now as a GPIO pin? Or do I want to use this pin now as a timer pin? Or as a PWM pin? Okay, some other functionality. So this is the actual GPIO port, actual pin layout for the microcontroller. Okay, and this is the mapping here. So you can see this is the mapping that the Arduino board gives you. So the Arduino board, so if you look back here, these pins down here that you see on the right side, 0 to 13, correct? The pins 0 to 13 are actually mapped to certain pins in your port D and certain pins in your port B. Okay, so they have already done some internal mapping for you, okay, so that it's easy for you to do it. Okay, so again, these details you will not know before this course, correct? Because previously you just say pin mode, certain pin, correct? Okay, so when you do pin mode, you do not know that you're actually controlling the microcontroller port B or port D. Okay, you are just looking at pin mode based on the pin of the Arduino Uno, but not at the microcontroller level. Okay, so that is what you must learn through this course here. Okay, so now come to the registers. So we talk about the registers in the microcontroller. So where do I get all this information? Okay, so all this information on the microcontroller is available through the data sheet of the microcontroller. So every time you buy a microcontroller data sheet, they will give you a very nice present, a few 100-page data sheet. Okay, so you can see down here, this one is 442 pages. Okay, so do we expect you to read all 442 pages? Of course no, I also haven't read before. Okay, but why do they give you all these pages? Because they want to make sure that you know or have the information on everything you need to know. Okay, so again, every microcontroller will have a very detailed data sheet given to you from the manufacturer. What you want to know is, at any point of time, what am I programming now? If I'm focusing on the GPIO, I want to go and look at the GPIO part. What are the registers? If I'm doing timer, I want to know what are the timer registers. Okay? So again, these are the ML, this is the ML datasheet. So you can see down here, for example, the pin configurations, how they are connected, okay, and how they are laid out. Okay, so let's go down to the GPIO section here, IO ports, okay, section 18 here. Okay, so you can see that it gives me all the details, okay, on what to program, how to program, okay. And this is quite interesting. This is the internal structure of a GPIO pin. So again, we are only looking at this single pin here. Okay, so as far as we know, we are looking at a particular pin over here. Okay, and that is the single pin that come out. But internal to the microcontroller, you have all this circuit here. Okay, again, why you have all this circuit? Because you are multiplexing so many functions, correct? Okay, that pin is the pin that only come out to the external world. But internally to the microcontroller, there's a lot of features that are hidden from you. Correct? All depend on how you select the register, how you activate the correct one that you want to use. Okay, so again, if I just come here, you can see down here that okay, so by reading this, you will have an idea how to configure the pin. So what does it say? It says that if I want to configure the pin, I must first configure the DDR register, correct? Okay, so it says that by configuring the DDR register, I can set the direction, whether it's going to be input or output pin, correct? Okay, so if a particular bit is set as 1, then it becomes an output pin. 0, then it's the input pin, correct? Okay, so that is what you can see down here. Okay, so again, all these are specific to microcontrollers, to different microcontroller. So do not assume that this is general, no. Every microcontroller, every brand may have their own logic. Some will say one is input, another one will say one is output. Okay, so these are the things you must remember. So in this particular microcontroller, they say that if I write a 1 to it, it is output. If I write a 0 to it, is input. Okay? Then, if I want to write to a register, I must write to the port X register. Okay? So again, they give you all this information. Okay, so again, why is this important? Because if you are going to work on a microcontroller that you have not studied before, then you need to go and look at this. Correct? This data sheet will give you the information on what you need to know to program the microcontroller. Okay? So coming back to our note, so of course here we are studying it, so we summarize and tell you what you need to know. So for a GPIO register, basically there are 3 registers that you need to deal with. Okay, your port register, your DDR register, and pin register. Okay, so if I want to configure the direction, I go to DDR. If I want to write to it, I go to port. If I want to read from it, I go to pin. So these are 3 registers I need to deal with, okay, for a GPIO port. Okay, so this is a simple code that tells you where or how do I set the direction. So for example, DDRB is a register. Okay, port DDRB is register. I must know what is the register address. Okay, so where do I get this register address? So again, in my data sheet, if I go down here, I can see my register summary here. And here I have the information on the register addresses for all the different registers. Okay, so every register also has an address. So when I know the address, I can write to the register. I can read from the register. Okay, so all of that is inside our data sheet. Okay, so inside data sheet, you can get all this information. Okay, so port DDRB, which is the data direction register for port B, is at address 24. Okay, and if I write a value 0 to it, means I'm making the whole port as an input port, correct? Okay, you have to remember this is an 8-bit port, correct? Okay, so DDRB is a register which is 8-bit. Okay, when I write a 0 to it means all of the bit got 0. That means the whole port B, everything is an input pin now. That means from port B, pin 0, from port to 1 all the way to port B, pin 7. Now it's an 8-bit port. Okay, that means all the pin now become input pin. Okay, how do I poll a GPIO pin? To poll a GPIO pin means what? That means you keep checking the pin until whether it become 1 or 0, correct? Okay, so when I want to do a poll, I must set it as an input output. Must be input, correct? If I want to poll a GPIO pin, that means maybe I connect a switch. I've connected a switch to a GPIO pin and I want to know whether this pin has become 1 or 0. So firstly, I must make sure that pin is set to input. To set to input, I must write a 0, correct? Alright, 0. So in this code here, what they have done is, they have configured a bit mask. So again, this is one of the techniques you can use, which is very good in making your code more readable. So this is a bit mask for bit 1. That means this hex-defined bit mask is giving me this particular bit pattern, correct? That means the least significant bit is 1, the rest of the bits are 0. Now when I do this, what am I doing? I am doing an AND of the direction register with the complement of bit 0 mask, correct? So the complement of bit 0 mask is what? 1, 1, 1, 1, 1, 1, 1, 0, correct? Okay, that means what? That means only bit 0 is a input pin, correct? Okay, and the rest of the pins are what? Input output. Bit 0 is now input, correct? Because I'm setting it to 0, correct? The other bits are input output. The rest of the bits I'm ending it with the logic 1, correct? So the rest of the bits, that means the rest of the pin from port PB1 all the way to PB7, is it going to be configured as input or output? How many say input? How many say output? Okay, so the answer is we do not know. Why we do not know? Why we do not know? Okay? Because it retains the value that it had before. It retains the value it had. You have to imagine that in this case, what's the difference? In this one here, what am I doing? I'm writing directly to all 8 bits. Correct? Here I'm writing directly to all 8 bits, so I can clearly say what is input, what is output. But in this example, I am not writing to 8 bits. I am reading the value, the current value, correct? And I'm doing an AND operation with this mask here. And AND with 1 means what? When you do an AND operation, you all remember AND gate or not? Don't tell me you forget. AND gate, remember CGs before somewhere? Or you burn and throw already the notes? Still have, Okay, so 0, 0, 0, 1, 1, 0, 1, 1, correct? Correct? So what does it do? When I end with a 1, what does it do? If one of the bits is already a 1, if it's a 0, it still becomes 0, correct? If it's a 1, it still becomes 1, correct? That means if I do an AND operation with a 1, I retain my original value, correct? I do an AND operation with a 1, I retain my original value, I never change. So that's why I said we do not know. Whatever was previously configured will still remain. Okay, so again, these are some of the things you must learn how to do. Okay, so again, CS 1010 you all have done, correct? Or some equivalent. So again, we are assuming you all are experts in C programming. Okay, so all this prior expectation is expectation, so you must have it. Okay, so once you configure, what do? You are reading. So this is the important part. This is the important part. So we saw DDRB direction, we saw port data. Okay, for port data is writing to this register is for the output. If I want to read from the register, is the pin register, input. So you have to remember there are two different registers. Total 3 registers. First register is for you to set direction. Okay, DDRB or DDRD or whatever. Your DDR register is to set direction. But for input or output is two separate registers. So again, physically it is still the same pin. Correct? As far as you are concerned, it is the same pin that I connect. Whether I connect a switch or whether I connect an LED, input or output doesn't matter. Physically it's the same pin. But as far as programming is concerned, it's two different registers. Okay, so if I want to write to it, if I configure it as an output and I want to write to it, I must write to this register, the port data register. If I configure it as an input and I want to read from it, I must read from the port pin register. Okay, so again, these are things, common mistakes you will do in your lab. Because you will try to read from the port register and you say the switch doesn't work. Then you go and change 10 different switches from the lab technician. Correct? And you blame the switch, you blame the resistor, you blame the breadboard. Okay, but actually you never set the correct register in your code. Okay, so when I want to read from it, I must read from the pin register, not the port register. So it's two different registers. Writing is a port register, port data register. Reading is the port pin register. Okay, so again, do not be concerned by this. You will have ample exercises in your lab to be familiarized with all of this. Okay, so again, we also have analog I/O in your Arduino. Okay, the analog is for us to do the input analog processing. We will learn how to do it, okay, in the Arduino in some of the labs, and we will also learn how to do some PWM coding, okay, with the variable resistor. Okay, so this one is using analog Arduino, okay, using our sketch library. Okay, so this one is using a sketch library where we do an analog read and analog write. Okay, actual programming we will also come to that along the way. Okay, so in summary, this lecture again we talk about the input output A to D PWM, plus we talk about the low level registers at the Arduino. Okay, so again you are expected to be comfortable with some of this. Your C programming you are expected to know, hardware interfacing you are expected to know. Okay, so again these are the expectations from you. Okay, the rest of it of course along the way we will teach you and we will guide you. Okay, so a few things before you leave. Okay, before you leave, the rest of this chapter got a lot of supplementary slides. That one you can go through on your own. Okay, that is to give you some primer in case you have forgotten or what is ADC, what is DAC, how some of these things work. You can go through on your own. We're not going to go through in detail here. If you haven't registered for your tutorial or lab group, please go ahead. And within your lab group, you need to find a partner. Okay, your lab work will be in pairs. Okay? By this week, once your grouping is finalized, I will send you an announcement to go and meet Mr. Tan Tim Fook from the Technical Services to draw out your board. Okay, so I will give you all a schedule. Please stick with the schedule to go and draw out your board. Okay, that is the Spark Fun Inventor Kit. Okay, so one group, that means two to a group. One group will draw out one box, and you need to bring that box along for all your labs. Can? Okay, so next week, labs will start, tutorial will start. All got marks, so please don't absent yourself and then you lose your mark for no reason. Okay, so please come. Your first lab manual is already uploaded, your tutorial also uploaded. Okay, so please have a look. You can go through and you can try. Okay, I'll see you all next week. Servo motor itself is the two variations. This one is just showing you that if I give this particular path, it will stay in this position. If I give this path, it will go to this position. But go, it will stay there. Yes. But again, there are different types of servo motors, so it doesn't go through.
thought when you register for the module, you were supposed to choose that. No.
As in, because this module wasn't in the balloting, right? So I forgot to check
I have no idea how you're supposed to do that.
because all the other modules are balloted. So I'll check. Mine just says not allocated. Yeah. Are y'all already?
Can you check with the undergrad office?
I see. Yeah,
I have no idea how to.
Mine, all the other modules are all done, but CG is just not allocated. So look at it. Email them.
So instead of doing a computer, why don't you just configure this with
So it's just
There's
no.
no reason.
It's all depend on your own personal style.
Oh. Thank you so much.
You are new. You previously. Oh, this is the one. I thought I see the If you don't have, you go to that first, and then you see who is If you don't have, then on the day you go. I think it's still open there. Then you just email the office.
How does this when you implement this in some 111, how why is the last one?
Because if you zero,
The last one.
no, they actually say that if a computer is zero, you DDR register, then that bit will become effective.
Okay. What's the
N operation is your.
control this table, the 1 0 1. So why you set the 1?
Yeah, because I already have a 1 here. So if my input is the other bit is the original bit here. Yeah, no, the original bit is DDR register. If the original bit is 0, you still be 0. If the original bit is 1, it's still 1. So by doing an AND operation of 1, you are retaining the original value that was in the register. You are not going to overwrite it. That is
So if it's 0, then you override.
no, when you do an AND operation with a 1, you are not changing anything. That is the whole idea.
Oh, okay. Alright, so it's follow this.
So the whole idea is I don't want to change what I don't want to change. I only want to change bit 0.
You only want to change second. Oh, okay. Input part.
Yes.
Okay. Thank you.
So isolated IOs means that the CPU needs to communicate with the intermediary.
No, isolated IO concept is basically like a Intel have separate address space, a separate instruction set and address space for each operating system. This is not like for example if you look at ARM processors for example, they have continuous address space. That means whether
Whether it's a data or
yeah,
instruction.
there is no differentiation. Anybody can use TV and all my code is also the same. But some processors, for example, Intel,
I see.
right now, yeah, that is just for, you're not going, that is a computer application.
Okay, okay.
This is just to show you what you
Primary, yeah.